Hello there, this is another lesson for Year 12 Further Maths, Exercise 6b. We're going to look at the chi-squared test with Yates' correction for 2 by 2 contingency tables. And you may recall, I've already shown you how to find chi-squared. There's two ways to do it. In class, I would have shown you how to do it on the calculator. And in the previous video, I showed you how to do this using the formula. And these two ways are great, unless they are 2 by 2 contingency tables, and there's a particular problem with 2 by 2 contingency tables. I'll read it out. It says the use of chi-squared will introduce some bias into the calculation, effectively making the chi-squared value too large, only a little bit too large, but too large. And to remove the bias, we use this Yates' correction. Now, I suppose what you've got to realise is whoever first, and I don't know who it was, thought of these contingency tables and invented chi-squared as a test for this idea of independence from the contingency tables. They did some maths and they effectively came across some formula. Whether it was proven or not, I don't know, but it's only a best fit. You see, what it does is experience has taught us that if the value is chi-squared is of a certain value, if it's too big, and again that's where the critical values come in. If it's too big, then we say, well, therefore they do seem to be, there's an association there. But if it's too small, we say it's there's no association. And where that probability lies, where those values should fall, is kind of being done by experience and probability to a certain extent. Now, this is suggesting with a 2 by 2 it doesn't work quite so well, and therefore we have to do this Yates' correction. I want to show you that now. So Yates' correction, of course, is something which happens with 2 by 2 contingency tables. So let's remind ourselves what a 2 by 2 contingency table is, and you should recall that you can see it's 2 down, 2 across. And we saw in class how to type these into our calculator. So the very first thing you have to do is get these numbers into our matrix. So I'm going to press second function, and then the matrix is actually above this one. So I'm going to do that now. So second function matrix, and it comes up with names math edit across the top. And let's write this here. So it's second, and then it's matrix. And you then go to edit. And when I go across to edit, I can then, I'm into A, it says A, and I'm going to say that's a 2 by 2. It might already be 2 by 2, so I'm pressing enter, and I type in 2, enter, 2, enter. And then it says, well, what are your numbers? So you might have some numbers there already. Mine is, I've used it before. So I've typed them in. And once you've done that, I tend to use the quit button. The quit button is just there. So I tend to write second function quit, just to get out of that mode. And then again, what I need to do is go to the the place where I can effectively do these tests. And to do that, you'll find you need to do, it's above the it says stat there. So I've lost my pen for a moment. So you'll need to press stat. And in that stat, you're going to, I'm going to press it now, stat, to go across to test, as I was saying. And then, you can either go up or down, but I tend to go up. And you'll see one of them that says C, and it says chi-squared test. And that's what you want. So I'm pressing that now. I've gone up to it and I pressed it, I press enter. And it says, where are you looking? Where's your observed data? And of course, I've already explained that this is our observed data. So I've said A. And where do you want us to put the answer? Well, the expected frequencies, if you like, are going to B. And then we just simply go down to calculate and let it do it. So then you press calculate. So I don't think I've shown you that on the video before, so it's probably useful that I've gone through it. And mine just says chi-squared equals, and it says 3.92. It tells me degrees of freedom is 1. We can worry about that later on. But you'll notice chi-squared then is 3.92, And what's the answer say? Oh, by the way, if we were doing this for real in the exam, we'd have to write out the hypotheses. And I've used two ways of doing it. It's either association or it's independence. The first one, these are independent of each other, or they're not independent. Now, of course, we've got the value of 3.92. What we'd have to do is look up a critical value. The degrees of freedom, it said on the calculator was 1, and you can use that. But you can also just use our formula. Remember, it was n minus 1 times by n minus 1, which in this case is 2 minus 1, which is obviously 1, 2 minus 1 again, so it's 1 times 1 is 1. So there's 1 degree of freedom. Now, you're meant to look up in the critical value table. Now, by now I've given you a critical value table. There's one in the textbook, there's one in the formula book as well, so it doesn't matter which one you use. And I'm just looking up on mine, critical value table for chi-squared, and so with 1 degree of freedom you have to go to the 0.95 column again where it says 3.841. So see if I agree with that in a bit, but this is obviously bigger than 3.841, which is the critical value. And because it's bigger, we end up, whenever it's bigger, you're allowed to reject H0. Now notice what H0 says. H0 says they're independent of each other. So we had, on our table, we had two things. We had the height and wealth. So we had height of people and wealth of people. And we've rejected this idea that they're independent. And that implies there's a link between them, a link between height and wealth, which explains differences that you might have expected. We would actually say there is, if you like, a link between them, a link between height and wealth. Now that's a link's not a very good way of writing it, but that's perhaps a way of describing it for us. Notice the posh way of saying it is they are not independent. We are saying there is a link. They're not independent of each other. That one affects the other. Now, if one affects the other, let's go back and look at our data. You know what? It doesn't seem very strong evidence. We've got 40 people who are rich and 35 who are short. It doesn't seem very much different. 50 people are short. A bit of difference there, but there's not an awful lot of difference between like all of these being 40, for instance. And clearly then it wouldn't have mattered at all if there's all 40. There would have been no difference. So it doesn't seem particularly strong evidence. And this, I suppose, is what Yates ended up concluding. On the face of it, the data does not feel strong enough to say there's a link. It's more likely for us to really be wanting to say there doesn't seem to be enough evidence to support this idea that they are not independent. So Yates's correction, what do you do? Well, you'll notice he basically introduced this extra value of 0.5. And when you do your O minus E calculation, you end up doing a subtraction. Now, bear in mind, the calculator does not use Yates's correction. Now this matters because it basically says if a 2 by 2 question comes up on an exam, if you do your 2 by 2 just by pressing the calculator button, which you very often you're expected to do on say a 3 by 3 or 3 by 2 or 4 by 2, if you use the calculator you'll get the wrong answer, and therefore be careful. So the calculator does not do it. We are going to have to use this formula. And notice there are two versions of this formula. This is the one which is actually the easiest one to use, which I probably will be using. And it's probably worth your while just writing it down. It's worth your while writing both down. You'll probably be given this one in the exam. I can't remember, to be honest. But definitely this one won't be in there. But this is the easiest way of doing it. So let's look at this data again. Of course, just now we got chi-squared to be 3.92, but I want to do this calculation again. We can't use a calculator. We already said that. We're going to have to do this properly. So very first thing we can do is actually use our calculator to get the expected values. You might be asked to show why the expected values are what they are. I'll just do this one. It might say find this expected value, and you might remember you add up the table. So that's 75, that's 80, that's 70 going across, and that's 85. And to get this first expected value, expected values, so I'm just going to draw up a table. It's rich, it's poor, it's tall, it's short. And to get this calculation, you do this 70 times the 75 divided by the total of them, and I think there's 155 in total. So notice I do 70 by 75 divided by 155. So if I just do that now, 70 times 75 divided by 155, and I get 33.9. So 33.9. Now you can cheat a bit. You can, if you, once you've typed them in, like I did before, you can look in B, matrix B. So I've gone to second function matrix and I press B, and it comes up with all the answers. So it's 33.9, and just I'm writing these straight from the calculator now, 41.1, and I've got 36.1, and I've got 43.9. Now that saves you a lot of work. Now I've written out a bit neater. I've written the original data, that's the observed data, and I've written out the expected data. And what I'm going to do is this O minus E minus the 0.5. Notice, by the way, that O minus E is in, it's the magnitude of it. Then you take away the 0.5, and then we're going to square it. And what you'll find is something quite weird. I'm going to do the first one, and the first one says O minus E, which is 40 minus the 33.9, and then take away the 0.5. That's the new bit. That's Yates' correction, and square your answer. So if I do that, I shall do it now. 40 minus 33.9 minus the 0.5, the Yates' correction. Press enter, and then square it. It says 5.6, so it's 5.6 squared. Oh, my calculator's trying to treat me here. 5.6 squared. Still struggling. 5.6 squared, and I get 31.36. Well, the reason why I think that's weird is because if I picked a different one, say I picked this one over here instead, doesn't matter which one I pick. So at this time, well, actually I'll pick this one because at least then it's the wrong way round. And the 30 minus 36.1, because it's the magnitude of it, let's do it the big one minus the small one. Then take away the 0.5 and then square it. And 36.1 minus the 30 minus the 0.5, look at that, it's still 5.6. So in actual fact, it's 5.6 squared, 31.36. All four of them will give me the same answers. And so that's saying to us it doesn't matter which way we do it. And then when you've got that, then the chi-squared is equal to that 31.36. Doesn't matter which one you do. You don't need four of them. All four are the same. You just need one of them. And then we times by, and then the trick is to do 1 over the expected values. And this time I do need them all. So it's 1 over 33.9 plus 1 over 36.1 plus 1 over the 41.1 plus 1 over the 43.9. So I'm going to type that into my calculator. 31.36 times by, and you might find actually you could got the x minus 1 button. I've just noticed I have got it. So you could use that instead. 33.9, 1 over it, plus 36.1, 1 over it, plus 41.1, 1 over that, plus 43.9, 1 over that, and then close the bracket, equals, and I get an answer of 3.27, which is definitely smaller. And of course at 3.27, which is, I'm hoping, the right answer, that is less than the critical value now, and this means we would not, this is do not now reject H0, which is perhaps a better fit for the data we had. It didn't look very strong data to conclude that there was a link between what the person's height and the person's wealth. But that's what chi-squared did before. So this is a better fit. This will give you better answers. Now I'm going to save this question for in the lesson. We'll start this here, and there's the answer as an exam question. And then we'll do in the lesson exercise 4b, and we'll practice this in class. So a bit convoluted, lots to do. We learned how to do it on the calculator if you couldn't remember, and we learned Yates' correction. Now we just need to practice it. Thank you very much.